Well, good afternoon, everyone. Welcome to Penn Engineering's fourth Joseph Bordogna Forum. It's a great pleasure to see all of you, especially after a great Super Bowl win. I was not expecting to. The closest I could get to midnight green is in my tie. So today we honor the legacy of Dr. Joseph Bordogna, one of the most esteemed leaders, a friend, a great contributor to the school and to the nation, and someone who's held impactful positions in the federal government throughout his life. I'm Vijay Kumar. I'm the Dean of the School of Engineering and Applied Science, and it's really a pleasure to moderate today's session. Before I introduce our distinguished guest, David Turk, and our co-panelist, Vanessa Chan, I would like to spend a few minutes talking about Dr. Bordogna, the person for whom this event is named. Dr. Bordogna earned both his bachelor's and his PhD degree from our school, and then a master's in electrical engineering and computer science from the Massachusetts Institute of Technology. After finishing his doctoral studies, he returned to join our faculty, first as an assistant professor in 1964, and then he went on to become the director of the then-named Moore School of Electrical Engineering. He then became an associate dean, and then finally Dr. Bordogna served as the dean of the school from 1981 to 1990. Throughout his career, especially at Penn, he worked tirelessly to increase the participation of underrepresented populations in science, technology, engineering, and mathematics education, and championed many initiatives that continue to impact our school today. Over 40 years ago, he established Penn Engineering's Office of Minority Programs, the first organization of its kind in our nation. And today, Penn Engineering is proud to continue this work in celebration of his legacy. In addition to his time in the school from 1991 until 2005, Dr. Bordogna served at the U.S. National Science Foundation, or NSF as short, first as the head of the Director of Engineering, and then the Deputy Director and the Chief Operating Officer of the National Science Foundation. Because of his time at NSF, where he worked to shape U.S. science and technology policy, I feel Dr. Bordogna would be particularly proud to have been here at today's event, which is called Creating Lastful Impact at the Interface of Energy, Technology, and Society. We're grateful, we're thankful today to have Dr. Bordogna's son, Ray Bordogna, who's in the audience, also a Penn Engineering alum. Thank you for being here, Ray. And we're also fortunate to have both David Turk and Vanessa Chan join us for this Joseph Bordogna Forum. And today we're discussing energy and climate change, one of the biggest challenges we face today at the nexus of technology and society. So let me first start by introducing both our panelists. First, David Turk. Throughout his career, David has been instrumental in shaping U.S. energy policy and advancing global clean energy efforts. Most recently, David served in the Biden administration as Deputy Secretary of the U.S. Department of Energy. And in this role, he was the Chief Operating Officer of a $50 billion per year organization focused on energy, basic science, and nuclear security. He played a leading role in implementing President Biden's clean energy initiatives, coordinating with the White House interagency partners and the private sector. He also focused on early-stage innovation, including the launch of a series of energy earthshots, which we'll ask him more about during our conversation. Prior to his nomination as the Deputy Secretary, David was the Deputy Executive Director of the International Energy Agency, where he focused on helping countries around the world to make progress on their clean energy transitions. He earned a bachelor's degree from the University of Illinois at Urbana-Champaign and a Juris Doctor from the University of Virginia School of Law. Vanessa Chan is no stranger to many of us, but I'll introduce her since she's coming back to Penn after a stint in Washington, D.C. She is the Jonathan and Linda Brassington Practice Professor in Materials Science and Engineering and the inaugural Vice Dean of Innovation and Entrepreneurship at Penn Engineering. Vanessa returns to campus after serving in the Biden administration as Chief Commercialization Officer and the Director of the Office of Technology Transfer at the Department of Energy. In this role, she was responsible for driving private sector uptake of clean energy technologies as the steward of commercialization activities across DOE. And not just across DOE, but also the 17 national laboratories and the DOE's other research and production facilities across the country. As a member of the Penn Engineering faculty, Vanessa has been a long-time partner in our growing engineering entrepreneurship program, and she has led senior design for material science and engineering among her many accomplishments. She's also an alumna of the school, where she earned a BSc in material science and engineering before going on to complete a PhD at the Massachusetts Institute of Technology. At this point, I'd like you to join me in welcoming both Vanessa and David to the stage. Very good. Thank you guys for joining. I'm going to start with some warm-up questions, easy questions, and then the questions will become harder, and then the final questions will come from the audience. We don't know what those are. I'll just say that many people in the audience, I want to say most people in the audience, don't have the pleasure of serving in the federal government, and they don't really know what it's all about. And some may not even be familiar with what DOE is. In fact, many might think it's the Department of Education, which is currently under attack. Hopefully the DOE is not. So I think it would be helpful for our audience first to know a little bit about what the Department of Energy is and what it actually does. And Dave, if you don't mind, I'll start with you.
Yeah, happy to do so. And I don't know if I've ever seen an audience all wearing similar color.
We planned it.
I heard there was a football game yesterday. Congratulations for those who are Eagles fans. Let me start, if I could, Vijay. Just I hope you all, at one point in your career, and it's just an honor to be here for the Joseph Bordogna and Ray, great to have you here, of course, as well. Just a career of public service. For some of us, I've now spent a few stints in public service in the government, and it may be that you're someone like Vanessa who takes phenomenal expertise in all sorts of areas and comes to the government for a few years, but just encourage you to at least consider public service in one form or another. It can be incredibly rewarding. So the Department of Energy is one of the cabinet departments in our system of government. It's a bit of an amalgamation in one of the more recent departments. So it was created as a department back in the Carter years. The oil embargo and prices were going up, and policymakers were like, holy crap, we probably should have an energy department and an energy strategy, so let's create a department. One of the parts of the department, it ends up being a pretty significant part of the funding of the department. About half of the funding or so is nuclear weapons. So we actually do all the nuclear weapons in many of our national laboratories, not the deployment and the decision of where to use those weapons, hopefully never use those weapons, but the development of it, and a lot of super smart scientists and physicists and others who do that. What's super exciting is we have two other missions, and you mentioned them, Vijay. One is the science mission. A lot of the science funding, and this is something that a lot of people don't know, a lot of the science funding doesn't just happen at the National NSF, National Science Foundation, but a lot of it actually happens about $8 billion a year. Now it's about $9 or $10 billion a year through the Department of Energy. And we've got these phenomenal laboratories all across the country where a lot of this science, this cutting-edge engineering happens. And then what's a bit of a misnomer, back when Carter created the Department of Energy, it really didn't have a lot of other tools in the tool belt to actually advance energy development, to actually get new types of energy, clean types of energy in particular, out there in the real world. And what's really exciting about what we did the last 4 years with the historic legislation that President Biden was able to pass is we now actually have a whole range of tools. I would argue for the first time we actually have a Department of Energy where we actually have the kinds of tools that Vanessa's team was wielding to try to advance commercialization, to try to make sure that we are actually benefiting from the technologies, not just in terms of use of solar PV and batteries and geothermal and all the other kinds of technologies, but the fact that we actually have a strategy, an industrial strategy to create those technologies, to get the economic benefits, the jobs benefits, and that's a lot of what we were working on the last 4 years. So that's a bit of a snapshot.
So Vanessa, in my introduction, I did say that you are responsible for commercialization activities across the DOE and the 17 national laboratories. What are the 17 national laboratories and how do they participate in commercialization?
Yeah, so for those of you who haven't actually heard about our 17 national laboratories, they are some of the most amazing places I've ever been to, and literally would make Tony Stark jealous in terms of the stuff that we have sitting in there. Many of you heard about fusion ignition happening. That was at our national laboratory. You may have heard about the fastest exascale computer, also a DOE national laboratory. In fact, 3 of the 5 fastest computers in the world are in our DOE national labs. And we do everything. In fact, oftentimes the secretary would joke we're the Department of Everything, because I would say that the cures for cancer are sitting in the national labs. When we were trying to figure out how to figure out some COVID vaccines, we actually used the national labs to really understand and study the actual COVID-19, which led to the development of the vaccine. The Human Genome Project started there. And so really what we have in the national labs are scientists and engineers, some of whom are Penn engineers, who are actually really pushing the forefront of research and development. And before this past administration, Biden-Harris administration, DOE is really focused on research and development. And then what happened was when we had Bill and IRA passed, we ended up getting $500 billion towards demonstration and deployment, which are the last 2 stages of commercialization. So commercialization went from research and development to demonstration to deployment. And now, what we were really focused on was how do we get all that amazing research and development across the 17 national labs actually out the door and into the real world. And so if any of you ever have a chance to visit the national labs, it's where we are doing the foremost battery research, we're doing hydrogen research, we're doing amazing things even to help Alaska. I have one of my friends here who works in the Alaska office, where we're even helping tribal nations figure out a lot of their challenges. And so in Alaska, with the cold climate, what are things we can do with building innovations? So if there's a problem you can think about in the world, there's a national lab within DOE that's really thinking about it.
Can I just pick up on something you
Sure.
said? You said $500 billion. I imagine that was the bipartisan infrastructure law, the IRA, and then the CHIPS Act, all of that combined. So tell us more about how that's been deployed and what impact it's having. And I'm going to ask you the same question, David.
Yeah, so it's actually been super exciting. And one of the things that we really focused on in this past administration was how do we use that money that was given to us to actually catalyze the private sector? Because in the end, $500 billion is a lot of money, but it's nothing compared to the $23 trillion that the private sector has. So if we're actually trying to commercialize a technology, in the end, it's not an institution like the government that does it. It's the private sector that does it. It's companies that do it. And so really what we want to do was have a private sector-led, government-enabled energy transition. And that was really the theme of what we were trying to do. So as an example, we had for every dollar that went out the door, $6 of private sector funding actually matched it, which is amazing. I'm sure many of you have heard about the hydrogen hubs that have been built across the nation. There's 7 of them. So there's an Office of Clean Energy Demonstrations, which actually had $8 billion to help seed the hydrogen hubs. We took $7 billion of that to actually seed 7 hubs across the nation, of which the Mid-Atlantic has one called Mach 2. And that $7 billion actually catalyzed $42 billion from the private sector to come to the table. And so this idea of a government-led but private sector-led government-enabled energy transition really has happened. And the other thing that we really were trying to do was figure out how do we actually catalyze the private sector to actually buy this stuff. So we took $1 billion of that and actually used it to drive offtake agreements, which the government has never done before. Because whenever you have a new technology going out the door, it's actually more expensive because of the fact we haven't yet scaled it. And if something is more expensive, no one wants to pay more for something. So what we're trying to do is figure out how do we make the demand and the supply meet to a place where there's actually offtake. And I'll use the other talking points that we always talk about in terms of the impact that we've had.
Yeah, so let me just give you, it's actually more than $500 billion, and it's quite remarkable just how historic the last 4 years have been, including and especially the legislative pieces. And that literally took decades and decades of advocacy. It took a lot of work by a lot of people to get us to that point. We can get into the question of, well, how much of this survives the Trump administration, and happy to give you my candid take on it. The answer, just to cut to the chase, is
I told you the questions have become tougher when you get to the Trump administration.
You're jumping to the extra credit already.
A lot of it does survive, and I'll explain why. It ends up being maybe useful to think of it in three different parts as an input, and then a couple outcomes, which I think are quite impressive, or outcomes in the making. On the input side, there are tax incentives. That's probably what most people think about when you think of the Inflation Reduction Act. 30% off if you're going to put solar, or you get $7,500 if you buy an EV, at least until and if that gets repealed. That ends up being something that doesn't get estimated. It gets estimated, but is not written in stone that it's a certain amount. It was estimated about $400 billion. There are some estimates that if consumers, companies, others use these tax credits, it could be $1 trillion. It could be more even in and of itself, and that leverages, as Vanessa said, 1 to 6 in terms of the private sector. So that's a huge, huge amount. That's the most we've certainly ever in our government. In fact, a lot of people have said, I think it's one of our favorite talking points, the Inflation Reduction Act was not only the biggest climate legislation ever in U.S. history, but the single biggest climate legislation ever in human history, just to give a sense of scale. So there's a tax credit piece of it. That in itself is a huge, huge deal. Second piece is the grant money. The hydrogen hubs that Vanessa was speaking about, that was grant money, cost share money that we were able to entice a lot more private sector investment and a lot of teamwork going forward. Just at the Department of Energy, that was about $100 billion ourselves, and some other agencies had some. Now, the good news there is we got most of that money out the door and committed. And so that is money already in the economy. That is money that is having its impact very difficult to claw back. And then the third piece is the loan program. So this is something that's been around for quite a few years, something that Elon Musk doesn't like to talk about, but he actually got a loan from the loan program to get Tesla through its critical early stages to become the company that it became. We got $108 billion committed out of that loan program, the most ever by far for the loan program, another couple $100 billion in the pipeline that I think actually will see the light of day, but another incredible tool. So that's the scale. You all, for those who are taxpayers or taxpayers to be, that is what you've invested in. That is what we bet on America in terms of our ability to help accelerate clean energy and climate. Now, a little bit on the outcome piece of it. What are we getting for that? For those who care about climate, and I consider myself very much in that category, we went with this investment, with the scale of this investment. When we came in, the Biden administration came in, our country was on about a 20% reduction in our emissions trajectory. So if you look at 2005 as the baseline, you look out to 2030, before all these pieces of legislation, we were tracking downward overall. That's great, but only a 20% reduction. That's not nearly where we need to be for those who are climate scientists who focus on these issues. We need to be about at a 50% reduction by 2030. With this legislation, these pieces of legislation, this volume of funding, this volume of support, the tools in the tool belt, the trajectory when we left office was to be at about a 40% reduction. So when people say you can't move the needle, you can't actually make progress, this is a direct data point that you actually can. The scale of investment, the scale of policy can move the needle on something like climate change, going from a 20% reduction to a 40% reduction. It also brought a huge wave of investment all across the country. Almost 1,000 new and expanded manufacturing facilities in the clean energy space, literally all across the country that have been spurred, that have been scented because of this volume of funding. Clean energy jobs are growing now, again, as we left office, twice as fast as jobs are growing around the country. That happens because you have a purposeful strategy, you have these incentives.
So just coming back to the one part of it is, of course, raising the $500 billion, and you're saying it's more than that. But the other part is to get private industry to, I think you mentioned 23 trillion. I think you said 6 to 1. I'm not sure which number is right. But what were the challenges in making that happen? The government's not great at catalyzing private investment, except through tax policy. So I just wonder how you've been thinking about this and how you thought about it and how you made that happen.
Yeah, maybe a few thoughts and turn it to Vanessa because she's done such remarkable work throughout her career exactly in this space. One thing, and this is first and foremost how the government works when it works, and suspect any organization, is hire people who know what they're doing. So it was a coup that we were able to bring Vanessa in for her period of public service in the U.S. government. But we brought in a whole bunch of other people who actually have done this in the private sector, have done it in the quote-unquote real world, trying to bring engineers together with people who know policy, who know finance, actually hire them not only so that they could administer and run these programs, but then they could go out and have very intensive conversations with industry, with investors, with others, so that it's not just throwing a bunch of money out there and hoping it works. It's actually doing the diligence, doing the hard work, getting the most leverage, like Vanessa was talking about with the hydrogen hubs. So first and foremost, it's the personnel piece and making sure you've got good, smart people who know what they're doing. And then secondly, it's just a lot of work to design and a lot of work to make sure that you're thinking about things holistically. The supply piece, the demand piece. You think about, well, what does this mean in terms of competition with China or others who are doing their own subsidies and their own investment? How do you think about trade policy and how that dovetails with what you're making in terms of domestic investments? And trying to put all that together, and the way we framed it and talked about it is actually having an industrial strategy. So not just hoping things work, but actually having a strategy. And it doesn't just mean you have a plan and implement the plan. It means you adjust, you learn, you talk to the private sector. You have a very intensive private-public series of conversations and partnership going forward.
Yeah, and so when I joined the administration, one of the things that was pretty shocking to me, and I use that word deliberately, is the way in which we do things in the private sector. Is the CEO, the chief strategy officer, chief technology officer, basically make a map of the world and be like, okay, here's how I want to win, and here's my strategy, here's how I differentiate myself. And then you figure out how much money you need to actually drive that strategy. But in the federal government, we actually are backwards, where the CFO is Congress, and they put money into the teams, who then have to decide what to do with the money that they were now given. In the private sector, we would never do it that way because it doesn't make sense. You need to have a plan before you fund it, but we do the opposite here in the US government. So it was clear to me we needed a plan with the private sector and what is it going to happen if we're getting all this money in. So my team at OTT quarterbacked an initiative called the Pathways to Commercial Liftoff. And they basically are commercialization roadmaps that we wrote with the private sector on what it will take to scale 13 different technologies. So we covered advanced nuclear, hydrogen, geothermal, carbon sequestration, like you name it, it's their virtual power plants. And what these are basically all the technical and commercialization barriers that have to be overcome, including things like unit economics, regulatory issues, supply chain, and so forth, that as an ecosystem, we actually have to tackle. And the reason why these were so critical is we had to get the entire nation on the same page of what are we going to do. So once we have the money coming in, right, the billions and billions of dollars coming in, how do we use it to catalyze where the risk is so high the private sector won't step in, but we can get to a point where we can get here, the private sector will take over. So it was a very deliberate effort that we put together within the DOE with the private sector in order to drive us there. And there was a lot of change management that was required even within DOE to do this. Because as I mentioned, DOE is really an R&D organization before the passage of bill and IRA and CHIPS and Science Act. And so we had to get people also on the same page in the government that the private sector needing to be able to make money when they commercialize technologies is okay. And that was something that was really, really hard to do from a cultural standpoint, but we got there. And so these liftoff reports, you can find them still at liftoff.energy.gov, and we've updated them along the way. That was another big thing that we did, was getting the White House and others to understand that when you commercialize something, you can put a roadmap together, but what you think was true now will not be true 18 months from now because things have evolved. So we updated the virtual power plant one, the hydrogen one, as well as the nuclear one, and hoping those will continue to be updated because what we need is like a single source of truth of the roadmap that we have together. And so that is, I think, really, really important, is being able to all sing from the same hymn book, and that's what these liftoff reports were.
I want to pick up on something you said, which is contrasting how government works with the private sector. So in the private sector, you imagine a company, and every 4 years you kind of fire the CEO, the CFO, and the management and start afresh again. This would be unthinkable, right? And yet it happens routinely in government. If you're lucky, it's every 8 years, but otherwise it's every 4 years. So I wonder if either of you could comment on that process, and then how do you work with that process with the completely different priorities of, let's say, a Biden-Harris administration with the current administration?
The questions are getting harder.
So maybe to
And this is my last question, then I'm going to turn it over to the really hard questions from the audience.
So maybe to start, heretofore, and I'd put this second Trump administration in its own special category, and we're only a few weeks in. I think it's important for us to realize we're only a few weeks in, and we'll see where things go from here. A lot of what the government has done and does continues from one administration to the other. Certainly that's the way the Department of Energy is. It's the same nerds working in a Democratic administration as the same nerds working in a Republican administration in our national labs and elsewhere. Sometimes the framing might be a little bit different. If you're in a Democratic administration, you may talk a little bit more about climate. And if you're in a Republican administration, you may talk a little bit more about resilience or reliability or something else. But a lot of the work continues. Now, the historic level of funding that we were just talking about the last 4 years, that is new. That is a dramatic increase in the tools in the tool belt in terms of folks working on things. But again, as I said at the very outset, like I have so much respect for the public servants, the civil servants who have made careers, some of them literally for decades, some of them for 10 years or whatever, nonpartisan folks trying to make sure they were doing right by their responsibilities, and at least heretofore, they just go to their job. Again, there might be a little change of focus. There might be a little different way of talking about it and framing it and work of it. I don't know why solving and curing cancer is not a completely bipartisan, nonpartisan issue. I don't know why solving something like climate change shouldn't be a completely nonpartisan, bipartisan answer. And I think we in our country's history for many, many years, for decades, for centuries, have had most of us are pragmatic. Most of us want to solve problems and roll up the sleeves and just get to work. And I think that's been a huge, huge strength. So even though the politics shifts and the news reporting out of D.C. has shifted dramatically, a lot of the work has happened, continues to happen, and again, with a bit of an asterisk in terms of what's going on right now.
And the thing I would add to that is some other impact that we've had. We've created over 900,000 jobs in the clean energy space. We've added, I believe the number is 20 Hoover dams, right, to the grid. Or was
30.
30 Hoover dams equivalent of new energy, right, to the grid,
so
which we need.
This is 2024, so this is 60 gigawatts of capacity. That's twice as much as we've ever put on in terms of clean energy onto our grid in our country's history. Again, that's the kind of thing that we should all feel a lot of pride.
And we need it because we have AI and data center growth going on and so forth. And, it's really important to understand that the majority of the federal government is made of people who are career feds, as they call it, and there will be continuity in the work that they're doing through that. The other thing I think that's important is in the CHIPS and Science Act, there was legislation to create DOE's foundation, the Foundation for Energy Security and Innovation, FESI. And my team was actually in statute to be the liaison to it and to actually establish it. And so in May of 2024, we created a board, which was chosen through a process where 13 people were brought on to run FESI as the board, and we were very clear it had to be bipartisan. So we have representation on that board from every single administration since George H. Bush, including 2 Trump appointees. Because in the end, commercialization, which is really what this foundation is supposed to work on, as well as supporting the mission of the department, is bipartisan. And we really do believe that it's good for the American people to be able to bring technologies to market. And if you look at the impact of where all the work this last administration has done has gone, it's 2 majority red states, although most of the U.S. right now is red in many ways. But it would be, as the Secretary used to put it, really malpractice, political malpractice, if we were to unwind that, because we have created jobs, we're catalyzing new economies, the 1,000 new plants and expanding manufacturing sites. I mean, that's real American competitiveness. And so I am hopeful that we're not going to undercut what we've built here because it's good for the American people.
Just to put a number on that, if I could, Vijay, there have been different estimates of how much of the funding through the tax incentives, the grants, the loans are going to red America versus blue America versus purple America. The number that we came up with 3 weeks ago at least was 80%. So 80% of that money going to congressional districts, going to states that are represented by Republicans. Having had a chance to travel to a lot of those cities, communities, I'm sure I was the only Democrat in some places that I went, being a Democratic appointee, a political appointee. Politics never came up. It was all about jobs. It was all about the community. It was all about this town having an opportunity to be successful and be competitive for the long haul. And the antibodies of someone in D.C. trying to snatch that away, snatch that bright future away, those hundreds, thousands, tens of thousands of jobs, I think that is political malpractice, political suicide. And so the antibodies will come out. There'll be a lot of discussions that are happening behind closed doors in heated kinds of ways going forward. And we'll have to see how that plays out. But that's a pretty significant dynamic I think we'll start seeing.
So I take that as a reassuring note. Let me turn the floor over for questions from the audience. Yes.
Well, first of all, I'd like to say thank you for speaking today. And I have a question for Mrs. Chan. I know there's a lot of talk about kind of grid scale changes and how we need to modernize the electrical grid before we can push a lot of newer technologies, such as electrical vehicles and higher demands and such. How do you go about commercializing those changes on such a large scale while keeping, I guess, continuity across the whole grid?
So great question. One of the liftoff reports was actually on innovative grid deployment. And what is really fascinating is there are actually technologies which work. For example, grid reconductoring, where you put new materials that make the grid's transmission more efficient. Dynamic line rating, where there's ways in which you can figure out how to smooth out demand and supply. And if utilities were willing to deploy this technology which works today, we actually could increase the capacity of our existing grid by 30%. And so if we're able to do that coupled with virtual power plants, and so what virtual power plants are, if say you have a school bus or a car which has bidirectional charging, which means that you basically charge it at nighttime when the demand on the grid is lower, and then you drive it to work, and then you charge your car battery to the grid, then that will allow you to help with the demand supply side of it. Those kinds of things can then buy us time to do some of the more earlier stage R&D things on the grid. And so I think that's what's really important, is that we have technologies that work, that we're not deploying. And tomorrow we actually have 3 people coming from the U.S. Department of Energy that also served with David and I, which is the head of the Loan Program Office, the head of the Grid Deployment Office, the head of the Manufacturing Energy Supply Chain. And that would be also a great question to ask Maria as well, because she's been thinking a lot about this. But I think really in the end, we have a lot of the work that needs to be done. There's a time series of how we have to do it. And if you look at the liftoff reports, we actually have one report that's around the demand on the grid and how the different technologies can meet the time series required as the demands on the grid increases.
It's a perfect question, if I could, of really showing the intersection of engineering, policy, and finance, and that you need super smart engineers working in laboratories and universities and elsewhere in private sector, developing the kinds of technologies that Vanessa's talking about, including a lot that are enabled or certainly helped by AI and machine learning and other kinds of cutting-edge technologies. But you also need the policy design, right? We are not a unified grid where there's some central headquarters in the U.S. where we determine this is how it's going to be and this is the mix. It's state by state, it's regional transmission organizations, and there's a lot of public policy in getting the incentives right, including the financial incentives to make sure you've got a stable grid, a reliable grid, an affordable grid. And then you have the investment side of things. You need to have decisions made by investors, by utilities, by others in the space. And we need people who can bridge those divide either themselves or work with others to make sure that we've got all these pieces together so that we actually get the benefits that we need out of our grid.
Awesome. Thank you. Questions at the back?
Okay, hello. I also just want to say thank you. But kind of adding on to Katya's question, just like you've talked a lot about new changes in how we finance innovation and the innovation itself, but is there like research and a lot of thought going into like policies and changes to our like political systems or like regulatory systems for infrastructure like the grid, where we have, like a lot of new generation, but maybe like not enough people working on how we can like physically hook that up to the grid.
Yes, so there's a ton of work going on in that space, and there's a real need for smart people, passionate people who want to make a difference in the world to get into that space going forward as well. So just a couple more granular examples of that. Right now, when you want to bring electricity onto the grid or you want to use electricity from the grid, you have to get into a queue. You have to get into a system in which you figure out how those electrons come on and how the system works out, and there's organizations that are set up to do that. We've had a challenge system, to say the least, in our country, and this is done decentralized all across the country in different places, where it's been first come, first out, right? First, whoever's in is the one who gets considered. In some cases, it takes 5, 6, 7 years. There's horror stories even longer than that going forward. And right now, there's a lot of innovation, including in the policy design, to try to cluster, to try to put some of these things together and make it a lot more efficient. So you can actually bring the kind of clean electricity on that you need to quickly to deal with climate change, but to have the economic competitiveness that we need, and to deal with the demand. For the first time in our country, for the first time in the last 15, 20 years, we actually have electricity demand increasing in our country. It's been relatively flat for the last 15 years because of efficiency and other kinds of things. But now AI, EVs, the manufacturing boom that we're having, electricity demand's going up. So you need people who are working on how do you figure out a system to bring that new electricity on in a way that works for the system, that has the right incentives going forward. It gets incredibly complicated, and you need people who can think technology, can think policy, can think how the private sector market works. But I think that's a terrific example of the kinds of multidisciplinary approaches that we need to have.
The other thing I'm going to add is that you have to look at the way that policy is done across the globe. Because I would say in EU and others, they like to use more of a stick, whereas we like more carrots here in the US. And when you take a look at a lot of new energy type of technologies, the other countries like in Europe are further ahead than us because of the mandates that are put in place by those governments. And that's fine, because what's happening is, in the end, if you're going to be creating wind or solar or whatever, you would need to get the learning curve, which means we need to deploy as quickly as possible. And if other countries are deploying ahead of us, we just have to take the learnings from there and bring it back into the US. And so I think in the end, policy, it's really, it depends on the country and what they're comfortable with. And there's things we can learn from each other in terms of the deployment that we have of new technologies.
There's a question in the back.
Hi, I just wanted to ask a question about carbon emissions. According to you, what strategies do you think are most effective when it comes to reducing carbon emissions on a larger scale?
Yeah, nice, easy question. So for those who follow this, won't be surprised to hear that not only in the US, but around the world, we're not on track. We're not anywhere near on track for the scale and pace of emission reductions that we need, right? Climate scientists have been telling us, including Michael Mann and other climate scientists, phenomenal climate scientists you all have here at the University of Pennsylvania, have been telling us for years, and it's only becoming louder and clearer, the upside risk, meaning it could be even worse than some of what our scientists have estimated going forward. We need to get to net zero global emissions in just a few decades period of time. That is a huge undertaking. This is one of the biggest transformations. It's both unnerving, but it's also exciting, especially for people who want to make a difference in their career and do something that's positive for the world going forward. One data point, other than just where we are on the emissions trajectory, emissions are still going up globally. They should be going down, and going down dramatically. And certainly richer countries, more advanced countries need to take the leadership role in order to really bend that curve and drive emissions downward. The kind of 40% trajectory reduction that we should be making in the US, it actually should be 50%. We need to bend it down even further than what we were able to do over the last few year period of time. When I worked at the International Energy Agency, Vijay noted before my most recent past job at the Department of Energy, I worked at an international organization, and we did analysis all around the world. And we broke up all energy systems, not just electricity, but transportation, buildings, across the board into 50 different sectors and specific technologies, and did an analysis of how many of those 50 sectors, technologies, are doing their share in terms of deployment, in terms of cost reductions, in terms of all the metrics you would want to look at to do their part to get us to that net zero in just a few decades period of time. How many of those 50 do you think were on track, were considered? There's a 0 there. Any other guesses that folks want to make? 0 is very pessimistic. There's a 5, I think, right there. Anyone else want to make a guess? There's a 10. Someone's optimistic, probably an Eagles fan after last night's victory. It ends up being 3. So 3 different technologies. Now, the good part of that is we actually can have technologies because of cost reductions, because of financial incentives. Solar PV is one of those technologies, by the way. The other good news is there's 47 other technologies that folks can get into, can have research into, so that we can have a full range of technology solutions for transportation, for buildings, for industry, for electricity across the board that's actually going to get us to decarbonize at the pace and scale that we need to. So the short answer to your question is we need a lot, and we actually need to build stuff too. To answer an earlier question of some of the challenges that we've had in the real world, it's permitting, it's actually getting some of this stuff out there in a reasonable amount of time period. One of the events that I can remember a couple years ago was in New York. They were bringing a new transmission system corridor down from Canada to take advantage of hydropower from Canada for New York City. I think it was about 15% or even a quarter of New York City's power was going to be clean energy because of this new transmission project. And so I was there with the governor and others celebrating this. And then someone mentioned that it took 17 years. 17 years in order to go from idea to actual fruition of this transmission project. That's not the scale, that's not the pace that's going to get it done in terms of getting what we need to get done in the US, let alone around the world as well. So there's a lot of people who need to work on the permitting space so that we can do the environmental protections, we can live our values, but we just need to do things quicker and at pace and scale.
I feel, Vanessa, this is a great time to ask you about this idea that you have about where people are ready to adopt new technologies or not. So 40% out of the 50 might not make it out of the gate because of your low adoption readiness levels. So this is a plug for you to
Perfect.
To talk about
so
your
one
work.
of the things that I found when I was at DOE was people use something called technology readiness levels in order to assess how close a technology is to actual commercial deployment. The problem with TRLs was it was invented by NASA in the 1970s to launch rockets to the moon. Now, if you're NASA in the 1970s, you don't care about the cost of the rocket. You don't care if you have to be able to make many of them. You don't care about getting a permit to actually land on the moon. And so using a TRL-9 as a proxy that now we actually can get this technology to market really was missing a whole host of things that we have to get right. And so what we did at OTT was we created something called adoption readiness levels, which is a complement to TRLs. And what adoption readiness levels does is it assesses risks around things like unit cost economics, regulatory, supply chain, even things like you may have a technology which is ready to go, but the community perception of it is really bad, so say nuclear, and people are not going to want it. Issues with demand where you might have the ability to create this, but you don't have the demand for people to actually buy it. And so there's 17 dimensions that we created, and it really is the language for how to actually commercialize technologies. And this actually has gone viral. We used it within DOE to manage our entire R&D and demonstration deployment portfolio. So many of the offices, like the Office of Clean Energy Demonstration, use it to manage their risks. But now NSF is using it, DOD, and venture capital firms are using it to assess whether or not they want to invest in technology, breakthrough energy, activate in a lot of the startups and so forth. And this is something I'll also be bringing to Penn, is the language of commercialization. So people are aware of the things besides technology that we have to tackle if something actually will make it to market.
We've got time for one more question.
Thank you so much for your time today. My question is, considering Project Stargate as well as just increasing data center growth, what do you reckon are some data center optimizations that can be deployed in the timescale that these data centers are going to be made? Because in my classes, I've learned about techniques like predictive ML for better workload scheduling, or like spatiotemporal
workload scheduling, as well as like more hardware-specific optimizations. But I wonder if this can be implemented in the same timescale, and I wonder like if this is something we should be worried about.
So that's a little bit over my skis, and I'm sure it's a bit over yours as well. But what I will say is that many of the companies that have the data centers and all that are looking at that, but also realizing that they need their own energy sources. And so one of the people that was on my team, Lucia Tian, has since left to run Google's team around building out clean energy sources to actually support the demand for the data centers, the AI and machine learning and all of that. And so it's a little bit of you want to be able to optimize things so you need less energy, but at the same time, given, my friend came over yesterday for the Super Bowl and she brought the perfect complement, like mac and cheese and an artichoke. I was like, this is a perfect, how'd you know to bring this? She's like, I put the Sign Up Genius thing into ChatGPT and they told me what to bring. So I'm like, people are using ChatGPT to do even things like that. And so I think just the use of AI, machine learning data and all that is just exponentially going to grow. So even though we're optimizing, I think the use of it is growing so much that we need to really figure out how do we do all of the above.
Yeah, just to elaborate a bit. One, I think it's really good to bring a rigor to what's going on with AI and data centers and how much electricity demand that'll be and what positives we can get out of that as well. One of our national labs, one of our 17 that Vanessa was speaking about, Lawrence Berkeley National Lab, I think is the foremost place to actually have good numbers, looking at the NVIDIA chips and other things that go into it about what we can expect and what are the uncertainty bands. So for those who are really interested, I encourage you to take a look at their latest analysis, which just came out about a month and a half ago on that front. Two, a lot of these big hyperscalers have very rigorous clean energy goals, like Microsoft, like Google, some others as well to varying degrees. We spent a lot of time, and I would hope that some of this work would continue from the government side, but certainly from the private sector side, to leverage that interest, their competitiveness, competitive imperative to bring those new data centers on as quickly as possible, but to really use that as a way to diversify and bring new clean energy generation and other technologies to the fore. So there have been a number of companies. Meta, Facebook, has a deal with a geothermal company, Sage Geosystems. Google actually has a deal with another geothermal company, Fervo. If we could take advantage of the heat beneath our feet, literally, and power 24/7 clean electricity and reduce those costs, move up that ARL, the adoption readiness level, that's a big, big win all around. And so there's a lot of conversations right now. We were trying to help facilitate a lot of those to try to help those hyperscalers get what they need, but have that be a positive to the overall grid, to the overall system. Lastly, there's a lot of work being done about how to operate those data centers that might actually be a little bit flexible, that could be part of the virtual power plants. Now, that may work for some applications, it may not work for others, but there's a lot of interesting research. And there's a whole area of research. I'm sure there's a lot going on here. I know there's a lot going on in other places, too, about how to leverage AI to its fullest to balance our grids, to improve the innovation cycle, so we get the benefits of that, including and especially on the climate side.
Perhaps I could ask one. We've got to wrap this up, sorry, but we do have a reception outside and you'll have a chance to talk to them. But maybe I can ask a question on behalf of all the students in the audience. If they want to have impact in the space the way you guys have had, what would be one piece of advice you would give them today?
So I might squeeze in a couple, if I could, Vijay.
Okay, two.
One is keep your aperture open on what you think you might want to do. I think it's kind of ridiculous, and maybe I was on one end of the spectrum where I didn't know what my life's plan was going to be. Some people know what they want to do very early on. If you fit into that category, I think you're quite fortunate, because others of us are not in that. But even if you're pretty certain you want to do this with your life, be open to new experiences. Have a bit of humility. Keep your aperture open. If you're a technologist and you're a hardcore engineer, think about maybe doing an internship on Capitol Hill for a year, or getting into the policy space, or working for an investor to see what the investment space looks like. Broaden your own horizons. I'm sure you're going to make you that much more successful if you have that perspective, if you have that opportunity. And you may find out that, boy, you might be a really good public policy person, or you really want to run for office yourself and put yourself out there We need more people in Congress, more people in the executive branch.
More engineers in
More
Congress,
engineers. We
Yes.
need more engineers. I don't know what the percentage of engineers are in Congress, but it's not nearly as high as it should be, certainly for Congress to make decisions that impact engineering, impact all the incredible work that you all are doing. So I would just keep the aperture open. The most interesting careers that I've found a lot of times are not linear careers. Someone has done this, someone has done this, and they've tried new things. They put themselves out there going forward. So I guess we'll just keep it at one.
Okay, good.
Yeah, and mine is going to be very, very, very tactical, which is when I was undergrad chair here a few years ago, people would come to me and say, I want to take 7 or 8 classes. And the reason why is they like to collect classes and say how hard it is. I would say to you, graduate the minimum number of classes that you need, and don't worry about GPA. It actually doesn't matter in the real world. In the real world, what actually matters is your ability to have conversations, come to these things, open your aperture, and to drive relationships and understand how the world works. So all of you guys should aspire to at least get 1 C. I really mean that because it is good for the soul.
I do not endorse that message, but that's fine.
Hey, I say my own thing because I really think that if you get a C, it gives you humility.
Yes.
It also gives you understanding that your world is not going to fall apart. Even if you get an F, your world is not going to fall apart. And so I encourage you to take the minimum number of classes you need to graduate and use that time to actually think about how you can have impact in your current ecosystem. Even though you are 17, 18 years old, you can make a difference in your ecosystem if you just stop trying to take 7 or 8 classes and get a perfect GPA. Mic drop right there.